2 less, but I'm not sure how to force people to show up. But to everyone else's detriment, they're not going to hear you speak. So Axel, hi, I can even name you. So Timothy, Anastasia, and Elvis, thanks for joining. So Axel is the head of a research group here in Germany, originally from Cameroon. And Axel and I have known each other a couple of different ways since 2016, but Axel is doing some really interesting work with data, applications of data. Yeah, I think he's really interested in passing on some of that knowledge, and especially the applications of knowledge to young learners or young researchers in Africa. And so today he's going to, I hope, do an introductory talk, but stimulate some curiosity. And I'm sure he will, if anyone is interested, he can go 1 step, 2 steps, 12 steps deeper. So as we're a small group, let's make use of the opportunity to make it interactive and ask questions.
Yeah, absolutely.
Yeah. All right.
Cool.
Thanks, Axel.
Hi, everyone. Sure. I'm Axel. So let me just start. Where is I'm sure I can present somewhere. Entire screen window. Let me see. Chrome tab. Let me see what we have here. I'm going to take this one. So the fundamental assumption here was simply that I am talking to people who have a master's degree in computer science, roughly. So basically, my fundamental assumption is that you're familiar with things like networks, that you're familiar with. Can you actually see my screen?
We can. Yeah.
Fact checking.
Yes.
Okay, fantastic. Yeah, that you're familiar with networks, that you have an idea of what a graph is, that you know what a directed, not directed graph is. And yeah, the rest is actually all derived from first principles. And that's actually really the message I want to pass on today. That a lot of the work you're going to see, and a lot of the work that actually has a lot of impact, is really just derived from first principles. And it makes sense when one is doing what is commonly known now as data science, to really try to get what those first principles are, because you can actually derive completely new ideas by just looking at what the fundamentals of the domain are in which you basically are doing your work. So what I'm going to talk about is fact checking. I'm going to try to tell you, number one, what knowledge graphs are, because we're going to talk about fact checking on knowledge graphs, and why knowledge graphs are important for you. Then I'm going to talk about a simple approach which is derived from first principles, but which actually currently performs best when it comes to actually checking the veracity of knowledge graphs, which I'm going to define as well. Does that sound cool? Have I said something that's unclear so far? Doesn't seem to be the case. Let's move on. Okay, so I believe in always giving credit where credit is due. So what I'm going to present is joint work with 2 of my PhD students, Michael Röder and Safa Syed, and it's heavily based on these 2 papers, a paper on corroborative paths for fact validation, and another paper which really looks at using textual evidence for fact validation, whereas given the time that we have, we're mostly going to focus on corroborative paths, but I'm more than happy to delve into the details, any technical detail you might be interested in. And warning, there are going to be some equations, but they're fun to look at. So first, let's begin by looking at knowledge graph. Why do you need them? Well, basically, knowledge graphs are a family of data representation mechanisms. And the reason why that's so interesting is that they're very flexible. You're most probably familiar with databases, and in databases, you have a fixed schema. You have a fixed schema, you basically put in your data. As soon as there's a change in the schema or in the semantics, you often have to rebuild the whole database, or at least alter it heavily. Knowledge graphs are used to represent data with a schema that changes frequently, and they're used by a large amount of very large companies simply because of that huge flexibility that comes about. And you use knowledge graphs every day. Every time you look for an entity in Google, for example, you basically query the Google Knowledge Graph, which is currently one of the largest instances of the Google knowledge knowledge graphs that we have. So if you query for Cameroon, for example, you will find that you have a bunch of text. This is standard information retrieval, but you also have this box. And this box really is nothing else than a rendition of the content of a knowledge graph. So your query is basically sent there. And the latest numbers that I've seen suggest that roughly 33% of the queries answered by Google are now answered by the Google Knowledge Graph and not by text search anymore. that makes it a very valuable asset. And it's not only valuable for Google, it's valuable for quite a few of the Fortune 500 companies on the planet. Internally, the knowledge graphs or good knowledge graphs look like this. So you have nodes, which we're going to call entities, and you have labeled edges. And the edges basically explicate the relationships between the nodes. It's actually very straightforward. You can load this with tons of semantics and so on. We're going to talk about some of the basics, but fundamentally, this is what one can imagine when one talks about the knowledge graph. So this would basically say something like, James has lived in the Eiffel Tower, was born on January 1st, 1984, and has visited the Louvre, where the Mona Lisa is, and so on and so forth. And as you can see, you can start answering rather complex questions using such a data structure. The major forces, i.e. the who of knowledge graphs, why are they so popular now? At ISWC 2019, 5 of the largest companies on the planet actually presented what they do with knowledge graphs, and that's basically just a photo that was taken during that discussion. And it's not because one did not have enough people to invite to this panel. Basically, all the major companies use knowledge graphs nowadays. And what they basically pointed to, and that was super interesting, was the amount of effort they put into making sure that their data is clean, i.e. that their data models the world we live in. So a fundamental assumption for veracity here is going to be that we have an objective definition of truth, i.e. A is married to B is a fact, even if it's temporally bounded, it's still a fact, or i.e. the person is either married with another person, A is either married to B or not married to B. We're not going to assume that we have a probabilistic view of veracity here, which one can assume, but basically for knowledge graphs, it makes things slightly trickier. In most real applications, work with the binary model of truth. Okay, so that's the who. What's the problem? The problem is really this, that if you are powerful enough these days, you can claim all kinds of nonsense. And yeah, it becomes an increasing problem if you really strive towards representing reality in your knowledge graph and not basically random claims. So the goal here is that given a data source, given a knowledge graph, we actually want to ensure that each and every fact, each and every statement in that knowledge graph reflects the reality that's around us. And if you look at very popular data sources like Wikipedia, we actually ran a corresponding experiment and figured out that somewhere between 15% and 25% of the facts that you can extract from Wikipedia are wrong. So, and there are tons of web pages which actually point to facts which were in the Wikipedia which were wrong, such as a lot of people who were claimed, or where the Wikipedia claimed that people were dead although they weren't, or lots of relationships which actually never existed, and so on and so forth. And we find that in a lot of data sets. So what we really want to do with knowledge graphs, given their importance, is have automated methods to actually check their veracity and, if possible, even correct facts which are found not to be a representation of the reality we live in. So fundamentally, that's the problem we want to address. I'm going to give you a running example, which is going to be this one. And I'm going to be very, very brief when it comes to technical detail, simply because we don't have time to go into all of that. But if you have questions, I'll be more than happy to delve into that. So one thing that's interesting in the Wikipedia, for example, so there is a knowledge graph which is extracted from Wikipedia, which is called DBpedia. And one thing that is quite interesting there is that Barack Obama has no nationality. So we have tons of information about Barack Obama, but there is no explicit fact which says that the nationality of Barack Obama is American. And you probably remember during the election, although you might be too young partly to remember that, how the claim was that he's actually Kenyan, he wasn't born in the States, he's not an American, and hence cannot run for presidency. So imagine that that were the case. So basically the fact Barack Obama nationality US American had to be checked. That's fundamentally the use case we're going to look at. How would we go about doing that? We first have to understand how knowledge graphs actually are structured. And in general, you have two types of facts in knowledge graphs. You have what we call assertional knowledge. Assertional knowledge basically just states facts from reality, something like Barack Obama's party is Democrats, and his birthplace is the city and county of Honolulu, which is part of Honolulu, which is part of the United States, and so on and so forth. So formally, what we're going to assume here is that we're dealing with a so-called hypergraph, and a hypergraph is a graph which is such that the edges connect more than two things. And here we're going to assume that edges connect three things, which is this particular subject, for example, Barack Obama, the relation birthplace, as well as the object of the fact, which in this case would be Honolulu. Okay, so that's the first type of statements we have in there. The second type of statement that we have in here, don't worry too much about the picture. Fundamentally, all this says is that in addition to assertional knowledge, you have terminological knowledge, and terminological knowledge is nothing else than your database schema. Fancy words mean simple things. It basically just tells you that you can give things types. You can say that Barack Obama is a person and that Honolulu is a city somewhere or an island, and things can have multiple types as well. Okay. So how do we go about addressing the fact-checking problem? There have been quite a few families of algorithms which basically said, okay, we are going to do that using text support. So what we're going to do is we're going to take the fact, say, for example, this is another example. Albert Einstein was awarded the Nobel Prize, but it would be the same if you said Barack Obama is an American citizen. You would take that, you would transform the entries in the knowledge graph into text and basically use a huge search engine to find text which corroborates that particular statement or actually goes against the statement, then use some form of scoring function, and then using machine learning, something like a feed-forward neural network, for example, that work pretty well, or J48 on decision trees also works pretty well here. You can basically confirm whether the fact is true or not. J48 means are you familiar with deep neural networks? Is it something that you've dealt with?
I think the majority of people probably not.
Okay, but I'm not going to delve into that too much, but fundamentally it's just a classifier. It's a function which, given a particular input, returns a value between 0 and 1, and that's basically what we use here for the fact confirmation. That works okay, but if we go back to my fundamental assumption at the beginning, which was that from first principles we can actually derive new solutions to existing problems, we actually tried that and we asked ourselves, what does it really mean from first principles if we want to check the veracity of a fact using a knowledge graph? What does it really mean fundamentally, or what are the restrictions we can derive with respect to the solution in that particular case? And if you think about any path, so any statement, something like Barack Obama was born or is a citizen of the United States, if you want to find other paths in the graph which corroborate that particular statement, because fundamentally that's what we're forced to do, you have some restrictions with respect to the source and the target of the path. And it's always going to be that the source and the target must abide by the same class restrictions as the path you're looking at. So if you think about the birthplace relation, for example, A was born in B, A will always be a person and B will always be some form of a location. There is no path that can corroborate the birthplace relation, which will not begin at a person and end at a place, right? That seems perfectly logical. That seems pretty obvious. But when you go from that fundamental really assumption, which is derived from the first principles of semantics and knowledge graphs, you basically end up with a quite interesting formulation of the problem, which starts like this. And this is where the equations begin, but actually super easy to understand. So we can derive what we call directed paths, which will denote pi k, or v0 vk. And all this says is really a directed path in a graph is a sequence of edges, of k edges really. We start at a node v0 and end at a node vk. And this is standard graph notation, so everybody should be familiar with that. And you can actually extend this to an undirected path sequence where you basically say that you don't follow the direction in the graph. I'll just give you an example to make this clear. So if you consider the graph you had at the beginning, you can say that in this graph there are directed paths, a directed path of length 2 between Barack Obama and the US, which is birthplace goes to Honolulu, or Hawaii, my apologies, birthplace goes to Hawaii, Hawaii goes to USA via the country relation, right? So that would be a directed path of length 2. You can also look at undirected paths of length 2, my apologies, and basically say there's the Greenwich High School. It is the alma mater of Barack, and the country is US. That's basically all we say here. And what we're trying to say now is if we want to check for nationality, we have to look for paths which abide by the type information that we have for the birthplace relation or for the nationality relation, which are such that they also abide by the type restrictions which we've set. And we can basically do that rather simply by saying that if we have directed paths or really paths, we can limit paths to have a certain type. So we can say we only look at types which start at a person and end at a place, for example. So we can define that formally by just saying that you remember that we had this directed path definition when we said pi k v0 vk is a path of length k between v0 and vk. We can say that we define a gamma function which just returns the types of the nodes, and the type of v0 must be an element of tx, and the type of vk must be an element of ty. And we then define the set of typed paths from tx to ty. Relatively obvious. Based on that, we can define Q-restricted paths. And Q-restricted paths are basically restricted, type-restricted paths, but that are such that in addition to saying where they start and where they end, we basically say which type of properties, which sequence of properties we want to have along that path. So which type sequence of edges we really want. So here we can say that we can have a Q-restricted path from person to place. Remember what we're trying to do here. And we can say that Q must be birthplace country. Then we basically say the first edge must be of type birthplace and the second edge must be of type country. So we basically say you have to connect persons and places using birthplace and countries. Why do we do that? Once we have this type of paths, all we really need to do to solve the fact-checking problem is count. It's really, really simple. We look at the edge that we're interested in this case, nationality. We say nationality always connects persons and locations. We now compute all the type paths of a predefined length n between persons and locations. We count the set of Q-restricted type paths which we have in there, and all we really need is a measure of common information, something like pointwise mutual information, to actually say whether a particular path corroborates a particular predicate. Once we have that, we use disjunctive probabilities, and we can actually then compute a score. The equations are here. They might not be that exciting, but really all they say is that we can use pointwise mutual information once we've counted the paths of a certain type which corroborate what we're looking for at the beginning anyway, which some, in this case, nationality. Totally straightforward. This is totally straightforward. This is derived from basic principles and from the most basic forms of probability theory. It's really nothing particularly fancy here, but this is not that important. It basically just tells you that you use the disjunctive equation for probabilities. What's important is the following. This table. This table says if you take this very basic solution and you compare it with the state of the art, you can outperform it significantly with respect to most of the significant tests that we have out there. And most importantly, your results also make sense. So you can actually look at these Q-restricted paths that you generated, and you can see that often if somebody's hometown is a particular location, then the person is very often you seem lost. I seem lost. I'm not sure I understand what that means.
Yeah, I think you can continue. I think one of the learners is saying she's a little bit lost in where things are going.
Oh, I see. We're basically almost at the end. All it says is we are looking for, if we're looking for the birthplace relation, all we really need to do, if we don't have the birthplace itself, is actually look at paths such as hometown, such as high school, parents, children, and look at that data. And that gives us information with respect to where somebody is most likely to be born. Same holds for other relations such as who's the CEO of a company and so on and so forth. Fundamentally, from basic principles, we can derive means to compute evidence or corroboration for particular statements using other statements which are ready to be found in the knowledge graph. And with that, we can actually address the fact checking, fact validation problem. And it is used in a lot of applications now. So for example, the Google Knowledge Graphs is starting to use statistical models to be checked. And those are 70 billion facts. So you can't really check those manually. We're currently thinking about applying it not to the Microsoft Activity Graph, but actually to the graph of the National Museum in London, because they also have a lot of fact information that needs to be checked. But other areas are so-called grassroots efforts, such as DBpedia and Wikidata, where such methods are used, also in applications in the biomedical domain. All right, so what was really my message? When you think about the area in which you are in data science, data-driven methods, you'll find that there are a lot of algorithms out there. There are lots of possible methods. There are a lot of libraries. And you can still make an impact simply by looking at the fundamentals and understanding the fundamentals of the domain in which you are, and really trying to rederive solutions from basic principles. And it turns out that when you do that well, you can actually create methods, create solutions which outperform what is available out there, even if that has been worked on for decades. That's fundamentally what I wanted to get at. And this was an example of how it has been done. I think, well, those were roughly 20 minutes, if I'm not mistaken.
Yeah, absolutely.
Axel,
Yes.
I want to say thank you.
Sure.
This is Yababa.
Hey, it's been a while. How are you doing?
It has been a while. No, it's great. And I can imagine some people are lost, and it's okay, because this thing is exciting, but at the same time, you don't have to understand everything. But I will ask a question. Probably some of them have worked on something that you may relate that to them with the context that you're talking. So they have done Twitter analysis.
Yeah.
And what they wanted to do was, of course, to identify communities within Twitter by kind of creating a graph who's talking what, and some similarities in their topic. So if you let's say, like, if someone wants to apply a similar methodology of searching, such that they apply based on similarities instead of now facts, but exactly the similar paths, what would be your advice where to start for them? Like, let's say, trying to apply this kind of methodology in relationships between people, as well as also between, what they are talking about. So,
okay. So Twitter analysis is a super interesting use case, and there are a lot of questions which are still completely open there. So it turns out that in Twitter, you have, first of all, different types of users. You have human users and you have bots. And amongst the bots, you also have what are often paid bots. And the paid bots are there to do a certain job. The job might be information. So there are so-called retweeting bots, which do nothing than scanning through content and retweeting content which might be of importance to a certain community, trying to establish themselves as hubs within the graph, if you look at it from a graph theoretical perspective. There are, however, also bots which are there for misinformation, which basically just generate stuff so as to establish themselves as interesting hubs, even if what they say has no validity in the real world. And there, again, these types of questions obviously come about. Now, there are a lot of different problems that one can then address using this method, which are questions such as, how do I classify hubs or nodes? That would be community detection, or basically type prediction. Then one can obviously ask the question, what are the intentions of the node? So basically, which community does the node want to be a hub in? That would basically be predicting actually edges in the graph. And you can obviously also ask the question, is whatever this node generates really genuine? Is it true, or is it just generated for particular purposes, such as rigging an election, which has been done in the past, but it was more on Facebook. And there, these methods can be applied. They would have to be extended, obviously, to the particular use case. Does that answer your question approximately, or can you? Or...
No, I mean it's great, because I mean what I want is exactly that, this relationship in their head to form from the example you gave, which is also easy, but in terms of like they have been working trying to identify that. So by like hearing example from you, I feel like they probably would understand the value of, you know, like why you need sometimes to do all these types of analysis, you know, why you need to subgraph the thing based on, you know, whatever you define types and classes. And that's why I just asked this question where, and then of course, if you think there is an exciting thing, we can definitely convert that also for them to start applying, like, because they have already got this downloading Twitter, analyzing Twitter. Of course, there is you know, there is, if there is anything you think exciting to try this method applying on that, we could also design some kind of challenge on that. But that's why I'm asking. But it definitely,
I think it's very exciting. So I was talking to the head of knowledge graphs, Jamie Taylor at Google, and they still don't have a solution they're completely happy with. The reason why this is exciting, if you think about 33% of the Google queries going to the knowledge graph, and they get, I think, 24 million queries per minute, something like that. I might be wrong. And then, but run the maths on 10 million. It means 3 million queries go to the knowledge graph. If the knowledge graph is correct at 85%, then you basically have 85, 2.45, 2.55, roughly 600,000 queries which return wrong answers every minute. If you were to be able to like lower that error by 10%, you'd be rich. Just to look at it from a rather mundane perspective, but it is a major problem. Most people on the planet use this technology without knowing it, and having an impact there would actually be pretty cool, both from a research perspective and actually from a practical perspective.
So we have also two questions, very, very interesting in the chat. One is saying like, why not Wikipedia using this to do fact check and correct their 15% thing down? What are the limitations of doing this? That's Emmanuel.
Sure. So we actually are, in the sense that I have to give you a bit of background. So if you look at Wikipedia, there are two major parts. You have these little boxes on the right-hand side, where you have factual information. That's basically where a lot of existing knowledge graphs derive information from, right? Because that's semi-structured. It's relatively easy to go from that box to actually generate portions of a knowledge graph. Once you've done that, you can then ask the question, okay, which of these facts are correct? And basically use a protocol, OAIE, MPH, to actually write back into Wikipedia and flag things. That's something you can do. That is something that you might not be allowed to do simply because bot editing Wikipedia is something that's not particularly well looked upon. Having said that, however, that there is a way to do it, and what people do now is that they do it on the knowledge graph side. So basically, you take Wikipedia, you extract the data, you run a fact checker on the data you've extracted, and then you have an enriched version of the knowledge graph, and you then run your application on the enriched version. So we're currently running a few research projects on the subject matter where the companies are really interested in doing that, or really are already doing that, because you basically can rely fully on the information on Wikipedia. But bot editing is still mildly frowned upon. The second reason why this is not used in Wikipedia is that parts of Wikipedia, and actually most of it, is text. So if you think about extracting a knowledge graph from text, you have 3 steps, which are entity recognition, disambiguation, and then relation extraction. And each of these steps is bound to make errors, to make mistakes. So if you then look at it from, if you look at the the amount of error that you basically have at the end of the pipeline, it basically grows with the sum of the errors across the, basically in the first factor, grows with the sum of the errors of each of the steps, which means that the knowledge graph which is extracted is not always the best representation of the text. And if you then do fact checking there, it might be that the reason why your facts are wrong are not Wikipedia itself, it's actually your extraction process. That is being worked upon, but I am not aware of a solution which can really pin down where the error comes from exactly, so as to say, okay, I'm not going to try to fix the text instead of fixing my software. That was between the text and the knowledge graph.
Okay. So, and then there is another one which is saying, when determining the degree, how do you weight them? The ages, sorry. When determining the ages, how do you weight them? For example, if you could use the Twitter community example. So
well, when you think about community detection, that is the interesting thing there. The edges don't really have a type. Okay, let me be precise here. The classical community detection problem is I'm given a graph. The graph might be directed or not, but I don't have types on the edges. And I'm basically trying to find a subgraph which is such that the elements of the subgraph belong to a particular community. And then I have different subforms thereof. What we're dealing with here are edges which actually are such that they have a type. And that's basically what we use, what we make use of. That's basically what I was saying, that we actually derive our algorithm from basic principles. Because let me just get back to the example I had. Maybe I'll go out of full screen to make this easier to swallow. Let me see here. If you think about the example, the basic example of a knowledge graph that I showed you, I didn't show you all the formal definition, but formally in a knowledge graph, the facts are such that the edge always has a type. And because the edge has a type, we actually make use of that, and we don't need to weight the edge per se. That was the formal definition that I gave you. But what we do need to do later, so once we have looked at the type restricted paths, so basically the different paths of different lengths which have certain types at the beginning and the end, what we do need to do is measure how correlated the path is with the property that we're trying to check. So if we go back to the nationality example here, and we think about the different paths which could potentially corroborate nationality, we have birthplace country, we have birthplace is part of country, we have party country, and we have alma mater or the inverse thereof country, right? These are different paths which are possible. And we need a weight here. We need to measure how much information of nationality is to be found into birthplace country as a path. And that we definitely do. And we do that using really point-wise mutual information, which looks at the...
Is that in the specification of the search that you have to, like in the choice of birthplace and country, that you will introduce the weight? Or is it, because once you specify what you are searching in the knowledge graph, is you don't have a weight, if I understand it correctly.
That is correct, yes, that is correct.
So, but to choose to kind of query that as a way of like checking confirmation, for example, for citizenship, then that is a pre-processing part where you need kind of to wait to choose that path with respect to another path. Is that what you're stating?
What I'm stating is that if I am given a fact such as Barack Obama nationality US, what I need to do is ask the question, how likely is a path to contain the same information as nationality, which is the edge type I'm looking for, right? And if you look at it from the point of view of statistics, what you're really asking is what is the point-wise mutual information, the mutual information between that path and what I'm looking at, right? So basically nationality in my example, which means that what I need to do is first ask the question, from first principles, only type paths of with a certain type at the beginning and the end can actually corroborate nationality in the example. So I first need to find those paths. Without any weights, all I really need to do is really count paths which are such that they start, begin and end at the right place, right? Once I have that, I can then ask the question, how much mutual information do I have? But given that I have the paths, all I really need to do is count. So I need to look at the joint probability divided by the probability of each of the paths, right? Or the path on the one hand and the probability on the other hand. That's basically how I compute my weights. And then when I have my weights, I can then look at the instance of the problem I'm looking at, which is Barack Obama in US in this case, and say, okay, I'm going to use the disjunctive, basically the disjunctive formula to take the point-wise mutual information which I had at the beginning and basically collate them to a single score.
So I want to ask a really dumb question. I mean, everyone knows that Obama was the president of the United States, so he's probably American. But why doesn't that come out in the data?
So why is it not in the data? Because it's not stated in the original data source, and that's exactly what we're interested in. So you'll find that there's a lot. It's not only that knowledge graphs are partly wrong, there's also tons of missing information. But if you're now trying to ask a question such as, was it legal for Obama to be president of the United States? Then if you formalize the problem, you say that one of the conditions is he must be a US national. And if you don't have that information, does it mean that the information is wrong? Or basically that that particular statement doesn't hold? So we have the so-called open world assumption when we think about knowledge graphs. So the fact that an edge is missing does not mean that that fact is wrong. It simply means that we don't know. And for such inference questions, especially in the legal domain, larger companies like Wolters Kluwer's, which they basically process tens of thousands of legal cases, they basically have exactly the same question. If I don't have it in my knowledge graph, do I have any piece of information that could help me assume that this is correct or incorrect so that I can actually go further with my case, right?
So if I put it into Google right now, what nationality is Barack Obama? I'm actually curious what it'll say.
It will probably say, we can actually try. You'll probably say American because that problem has been fixed since then, right? Let me just see. If it's just say nationality Barack Obama, I should actually get American.
It doesn't say in the...
It doesn't say. It says he's the only president born outside the contiguous 48 states. Interesting. Yeah, it actually doesn't tell you. But then you would basically want to have such a fact-checking algorithm on the Google Knowledge Graph to actually say, all right, can I actually give you paths? And that's what I showed you in the example at the end. Can I give you paths which basically corroborate that he's most probably American, which is what the end user actually wants to see, right? The end user is not, in general, the end user is not interested in a bunch of text. The end user wants an answer to his or her question. And you could say, I assume he's American because he was born in Hawaii, and Hawaii is part of the US. His children are American. His wife is American. His parents were American, at least one of his parents. He went to a high school in the States. He did his studies in the States and so on and so forth.
But I think you already mentioned it. All that doesn't mean you can have a million corroborative evidence, but if it's not a direct evidence, sometimes it's the same.
Of course. So this is exactly the reason why these are called corroborations. They are by no means a confirmation of the fact. Those are basically very different things. But in general, if you think about knowledge graphs, what I did not talk about is really the formal logics behind knowledge graphs. And when you build a knowledge graph, in the schema, you basically write down axioms, right? You basically write domain axioms, which basically describe how you can infer new knowledge from the facts that you have. And if you could already infer that Barack Obama were an American national, you wouldn't need fact-checking. So in general, you will assume that you've run your inference engine and you've queried the inference engine. The inference engine says, I do not know. I have no answer for you. And that's basically when you go like, okay, I have no way to confirm the fact. Hence, I have to go for, do I have anything that corroborates my assumption?
Okay, so I think we're coming close to time. Are there there's one last question or one question. Elvis is asking if there are any places you can point learners to where they could learn more about this? Any resources, websites,
Of
etc.?
course. So basically, if you were to read, to look at the papers which are at the beginning, that's why they're in the slides, you'll basically find all the formal definitions, how the algorithms work under the hood. And the first paper is really about corroborative paths, what I talked about today. The second paper is more about using a text-driven approach to address the same problem. Most importantly, in the list of references, you'll find tons of papers which actually address the problem of fact-checking from different perspectives.
Are you able to share the slides with us? We could pass them on to the learners.
Of course, no problem.
Okay.
I mean, I might have to ask Misha and Safa first whether they're fine with having their pictures and slides, but I don't think they have any major problem with it, so it should be fine. Oh, those are on the website, so they're fine anyway. It's public content now.
Okay. Okay. Any last question? Any one person last question?
Ooh, I see a link to the Google Knowledge Graph here, search API. Cool. Yeah, you can use that for experiments for fun.
Evan?
Great, thanks a lot. I think that's it. Kind of really is good if we could devise a little bit kind of a challenge how you can apply a reduced version of the algorithm to Twitter. That would be nice.
But do you really want to go Twitter on this one?
Because I feel like, so there is a relationship between users and their texts through different, what you call class. So followers relationship. So that's the kind of what I think is what you could consider class or friendship and like, and there are many paths that you could construct from one person to another, but how you reach it is different. So if there is a way, for example, to quantify within a given keyword you searched, if you could decompose it into the same formalism and then try to query that formalism.
So if you're thinking about doing node classification, that could work. But anyway, we'll have to talk about the details.
We'll just, I mean, I'm just, again,
it's quite different.
Exactly. I'm off the, the brain, just on top of my brain. I don't think, sometimes maybe it just, I didn't understand clearly the details. But I just thought like, that would be something they have done already. And it's something we can build on top, just one way or another. But definitely, let's talk.
Absolutely.
Yeah.
Thanks, Axel. Thanks for your bringing perspective to it. I think you've been able to reduce the complexity of what you're doing significantly. So we appreciate that. I see Gerald is making suggestions on how we can go forward with the challenge, but we'll share the slides. But thanks for taking the time. I think that for many of the learners, what you've presented is sort of a couple of steps where the work that you're doing is really data science applied to the real world, optimized at production level. So I think there are many different layers to the work that you're doing. But thanks for sharing kind of a very first level view of the work that you're doing. We will post the video for the use of our learners here. And thanks for the time. And I'm sure, as the other was saying, we'll reach back out and see if we can work together to give some good data to come up with a good challenge.
Sure, we'd love to do that. So thank you all for taking the time to be here, and talk to us soon, I hope.
All right. Thanks so much.
Cheers.
Thank you.